Yeah, good afternoon, it's Charlie ZL2CTM. Right, so what I'd like to do today is do the second part of that two-part video looking at the VFO. So what I want to have a look at is the software side of the house required to drive the display, read the rotary encoder, read the band switch, and then send the necessary commands through to the SI5351. So before looking at the schematic, so what we have here, we've got the display down here, we've got the rotary encoder, which changes the frequency. You can see there's an underscore there. That's what I typically use for this type of display to indicate which digit is being changed. If I was to push down the rotary encoder switch here, push it down and hold it down and then rotate it, you'll see that cursor move left and right. And when I release the switch and I turn again, that's the frequency that's the digit, more the point, that's now been changed. I quite like that way of displaying it, as opposed to having over here, say, 100 kilohertz or 1 megahertz or 1 hertz or whatever, what I have called in the software the radix is at the moment. There's also a mode switch here, so when you flick the mode switch to 40 meters, it brings up what was the old 40 meter frequency. And of course we can now change that. So if we were to set that on 712, rotate 3, if we now go back to 80 meters, it's retained the old 80 meter frequency. If I go back to 40 meters, then that's retained. So we'll look at that software as well. And that's it. So that's all I wanted to cover off. So from a schematic point of view, it's pretty straightforward, which is nice and easy. So I've just updated that bit of paper I had the other day that looked at the SI5351. Let me just get a pencil here. So like the SI5351, that I2T ICE, or that liquid crystal display down here, is using the I2C data bus to talk to it. So the good thing is there's only two lines. On the back of this particular display is a little piggyback daughter board, I guess, which converts the traditional 16 pin layout from these particular displays to 4 pins. So it's an I2C to 16 pin converter, which makes life a heck of a lot easier in terms of wiring. So you can see those 4 pins there, or the SCL, so the clock, the data, the SDA, the I2C, and then the VCC in the ground. And they are wired directly in parallel with the SI5351 going to those same pins we looked at the other day. So nothing difficult there at all. And then from the switch side of the point, or from the switch side of the house, we have the rotary encoder. Now the rotary encoder, if you were to look top down, has 5 pins. On one side there's 3 pins, and on the other side is 2 pins, is the standard configuration. These 2 pins down here are just like any other momentary switch. You push that button down like that, push, and then these 2 here get made, so they get closed. Up here, these 3 pins here are basically the pulses, or the little short earths that the rotary encoder sends out that need to be read and interpreted. So the configuration for that is the center one goes to ground, and then the other 2 go to the board. So that's what you see there. And then the other switch here is that mode switch between 80 meters and 40 meters. Just a simple switch there, either supplying nothing in terms of, or an open circuit to pin 5, or a ground to pin 5. And we'll see in the software later on how that's being read and how that's being interpreted. So in terms of the individual pins for the rotary encoder over here, the push button switch, one side goes to earth. So when you push that switch down, that earthing gets applied to pin 4 through the internal switch. And on the other side, those 2 output pins from the rotary encoder go to pins 2 and pins 3 in the code that I've got. And like I just mentioned before, that band switch goes to pin 5. So that's all I wanted to cover off from there. What I'll do now, I'll just break this video, and I will endeavour to use the inbuilt software for recording the screen in Windows 10 to carry on. So hopefully, I know the audio is a little bit different, but hopefully it'll be clear enough to understand what's going on. So give me 2 seconds. Okay, so hopefully that's coming through. I'm conscious that the video, also again the audio is not the best, but it will have to do. Hopefully I'll be able to get across how this software is set up for me. I do need to say that there are different ways of doing, say, the SI5351 and the rotary encoder, especially the rotary encoder. What I'll show here I've been using for quite a long time now. I have looked more recently at other ways of doing the rotary encoder, but I found this, for me personally, to be the best for me. It's not that won't be the case for others, and I totally acknowledge that. But at the end of the day, this is what I have done, and I'm comfortable, and this is how I'm going to run with it. Okay, so starting at the top, and hopefully this won't take too long. We have our two libraries. So the liquid crystal display library there is for obviously the display. It's the I2C version there. And then the second library is the SI5351 library. And as I mentioned in the video just before this one, I'm using Jason Mildren's the EtherKit library. For me, that works really well, and for now, that's what I'm sticking with. We have a series of constants here and variables that are used for mainly the frequency and the band. These four here, the band starts and ends for both 80 and 40. When I'm changing the frequency, I'm checking that I'm not going to go beyond the end of a band, or if I'm going down in frequency, I just double check that I don't go below the start of the individual bands, either 80 meters or 40 meters. So for your regions, if you have different band limits, then this is where you change it, and the code will just run from there. This is the main frequency variable that gets updated as the rotary encoder gets changed, and that holds the frequency. We've got the radix here, that's the current increment value, I guess, when you change the frequency, and it defaults to 1 kilohertz. And then some variables here that hold the old frequency when you're changing modes. I won't go into these ones here, they'll become self-evident as we go through. The band variable here holds what the current band is. So if there's a 0 for that particular variable, it's 80 meters. Otherwise, if that pin is earthed, then it basically detects it's on 40 meters. I did play around with having that actually being 80 and 40, but you know, I did double check it. It didn't work very well, so I went back to this simple way that, like I say, it's rock solid and works well. We've got some variables here that are used to store what's going on. Or in fact, more the point, sorry, these actually define what the various pins are. This one here is for the rotary encoder. You mentioned, if you recall back to that circuit diagram, those two rotary encoder pins, 2 and 3, and then that push button switch sitting on 4, and then that should actually say band, not mode. That band switch, singular, is sitting on pin number 5. Right, and what I was going to say just before is here goes the variables here that set what the current state is for the rotary encoder. Okay, so having done that, so we'll load up the libraries, we've defined some variables that we'll need. The next thing is to instantiate the two objects, so to create the two objects, one for the crystal display, which we're going to refer to as LCD, and then the SI5351, which we use a nice novel name, SI5351. So when we want to send commands to those two devices, we'll be using the LCD dot something and then SI5351 dot something. In the setup here, and I apologise if this is going way too deep, feel free to skip this part here, but I know there are people who have asked me to go into a little bit more depth with regards to the software, so I will go through pretty well sort of line by line, but like I say, if you're all over this, just skip through the end. Okay, so we're in the setup here, so we need to set up our digital pins. So that's what the pin mode is here, and I'm setting up those two rotary encoder pins, the push button switch off the rotary encoder, and the band switch to be all inputs. And then I know there's different ways of doing this, but this is the way I do it. Digital write those same pins high. So I'm basically enabling the pull-up resistors. So As you apply an earth or a low, you then pull those down, and that's what gets read by the microprocessor. So they default high, or being pulled high by the internal pull-up resistors. Now, what I do like about this particular code down here, and I must admit, and I mentioned this way back when I first started using this code, this is not my code. I didn't come up with this particular way of doing the rotary encoder. I honestly can't remember where it came from, so I can't actually provide credit to the person who wrote it. But I will say, for me, it's nice and rock solid, it's nice and responsive, and I don't have, which I have had in the past with other ways of reading the rotary encoder, lags and delays. Anyway, suffice to say, those pins 2 and pin 3 for the rotary encoder need to be interrupt enabled pins, because we're going to be using 2 interrupt service routines, 2 ISRs. That's what the ISR stands for there, interrupt service routine, to basically get enacted when those 2 pins 2 and 3, receive a change state. In this particular case, it's change state there. So whenever those pins change, the interrupt gets basically fired or gets triggered, and then these 2 interrupt service routines get run, which we'll see later on. So we need to set up those here within the setup portion of the sketch. We need to initialize the display, so dot begin, turn on the backlight, and then set the cursor, because I'm using that cursor to determine whereabouts the radix is. And then I go on to initialize the DDS, so the SI5351, probably better if actually said that, wouldn't it? 5351, a bit more clear, or a bit clearer I should say. We initialize it, and here goes that set correction factor. So that's the one we came up with yesterday, so it had 191, quite interesting. So what this basically means is that this code now with 191 is now tied to that particular SI5351 board that I calibrated yesterday. And to be fair, any temperature variations, things will change, but that's why I tried to sort of soak it to be, from a temperature point of view, about where my shack normally sits. If I hadn't calibrated this, in other words, if I don't include this, honestly, the output is still pretty close to the desired frequency. But if you want to be smack on, then it certainly is worth calibrating the SI5351, determine what that correction factor is, and then use it in any sketch that you're using for that particular board, noting temperature variations, and potentially, and I don't know this for sure, if I have huge amounts of code down here that are potentially playing around and impacting the I2C, there's other things that could potentially go on. I don't want to say any more about that one because I don't know enough to say any more. Couple more lines that are required to set up the SI5351. This one's pretty well just a stock standard normal one, and then this line here is quite important. More so this value down the end. You've got a choice of 8 milliamps, 4 milliamps, and if I recall, so 4 you can use, and 6. So I use 8 milliamps, and that is the drive level. So that's let's say the amplitude of the SI5351 output. For the SBL1 and the Homebrew mixes that I'm making, 8 milliamps is just fine. However, if you're using some of the smaller devices, like if I recall, the ADE-1 and that'll need to be a lot lower, more like 6 and 4. So just be careful there, because you don't want to burn out if you're connecting the SI5351 directly to the mixer. Anyway. So having now initialized both the display and the SI5351, I'm then just racing away and I'm updating the display to make sure the display is reading the default settings, and then I also just make sure that the SI5351 is outputting the right frequency, and we'll see these two functions that are further down later on. Okay, then we've got the main loop. So this is the one that goes around, 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 around all the time. The only time that this main loop is interrupted is if those two interrupt pins get triggered by a change, and then the two ISRs run. But if nobody's playing with the rotary encoder, then this loop here just goes around, 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 just checking. First things first, again, I inherited this code, so it works for me. I fully acknowledge there's other ways of doing business, but for me it works, so this is what I'm presenting here. I need a nice friendly way of checking to see what the current frequency is, because if the current frequency is not equal to the old frequency, then basically someone's been rotating the, well, I say someone, I have been rotating the rotary encoder to change the frequency. So if that's the case, I then want to update the display. I want to send the new frequency as an output, and then I want to make the old frequency equal the current frequency. And I do that because the next time I go through this, I want to be able to see if the frequency has changed yet again. So this current frequency equals get frequency brackets brackets open close. So that's a function, and that's down here. So get frequency, turning off the interrupts. We're getting as a temporary frequency what our current frequency is, turning the interrupts back on again, and then returning that value. So that value there, which now equals frequency, which we'll see further on down has just been changed by the rotary encoder, gets fed back to the main loop and becomes current frequency. And then it's current frequency, then it gets checked to see if something has changed. So that's what's going on there. Assuming that's all been carried out, the next part of the for loop, I'll say again the main loop that is checking the digital read or the rotary encoder push switch to see if it's been pushed in, and that's the low there, remember. So if that's just like a normal momentary switch. If you push it down, then that earth gets fed through the switch and gets fed to pin 4 that we had assigned here. So that's what we're testing for. If that's the case, the reason why I had to insert this here is I needed a way of stopping the frequency display from flickering when the radix was being changed. So all this is doing here is just making sure that the display, the frequency doesn't change while I'm changing the radix. That's all this part here is doing. We also need to check, or the next thing that gets checked through that main loop is to see if the band switch has changed. So it does a quick read of the band switch to see if it's low. If you recall, if it's low, it means that it's on 40 meters. And otherwise, if it's not low, then it's on 80 meters. Like I say, before I did try having this band equals 40 for 40, and ours band equals 80 for 80. But it was not playing ball, and you know, I spent sort of 10 minutes on it, couldn't work out what was going on, so I just defaulted back to this. You know, right or wrong, I'm happy with it. It works. Very similar to the frequency. So if the band has changed, so that band switch has been moved either to 40 or back to 80, this test here gets, or this if loop, more the point, gets actioned if that has changed. That's what that not equals to. So if band is not, exclamation mark equals old band. So that's the same up here, not equal to. So if it's not equal, then it goes here and does a check. Does the band equal 0? If it is 0, it means it's now 80 meters and it was 40. So that's the case. We want to, because we're now moving to the 80 meter, we want to make sure that the old 40 meter frequency, so sort of a bit like a memory, equals our current frequency. And then we assign the current frequency to equal what was the old 80 meter frequency. So we're doing a swap there and just making sure that things get stored away. Conversely, if the mode, say again, the band switch goes the other way, so it was 80 and now becomes 40, then we want to store away the old 80 meter frequency so we can use it next time the band switch gets switched. So old 80 becomes frequency, and then the frequency then becomes what was the old 80. And of course, what this is was up here. So in other words, we're just swapping things around. Having done that, we update the display to make sure everything's all nice and tickety-boo. And then the next time through the loop, the frequency will be sent because it will realise that the frequency has changed. And of course, just making sure that the old band now equals the current band. So when you go back through, if things have changed, this will be triggered again. And that's it. So that's all that's going on in the main loop for this particular VFO. So from this point onwards, moving down are going to be the various functions that are called by virtue of the main loop requesting something. I'm trying to keep sort of simple language here, so it's not strictly correct, but you know, I'm trying to use easy to understand language. So we talked about what that get frequency is. We don't need to talk about that one. And here goes our two interrupt service routines. So these two routines get called, either this one or this one down here, when the pin changes on the rotary encoder. So that's pins 2 and 3. So me, is rotating the rotary encoder. I've fired off the interrupt, so the interrupt's been tripped, and it's now, depending on which interrupt gets tripped, determines which interrupt service routine gets enacted. So you can see the ISR wrote, so it's rotary encoder A change or B change, and if we were just to nip back up there just to show where they were, here they are there. So here goes when I was setting up those two interrupts, there goes the two interrupt service routines. So all that does, let's just say for example the A pin had changed, then it does a quick read. So the digital reads what is that pin, and it basically goes, okay, so it basically if it's 1, it gets set here and then goes and runs the update bit. Otherwise, if it was a 0, it gets set here and also runs away and does the update rotary encoder function. So get a bit tongue-tied there, sorry. And exactly the same if the B pin had been tripped, the interrupt looking at the B pin on that rotary encoder. Gosh, I hope that was clear enough. Suffice to say, after doing those two reads and then setting those two initial variables, depending on which one's which, it then rushes away and runs this particular function, which is just sitting right below it. Here it is here. Now this is the one that I inherited, so I am not going to attempt to describe exactly what's going on here. I will say, if you go onto the internet and you look up how does a rotary encoder work, you will see all sorts of timing diagrams that go to great lengths in describing in terms of if one pin is high and one pin is low and then one pin goes the other way around, etc., what's actually happening. So all I'm going to say here is this update rotary encoder function, which is this part here, all it's doing is it's basically determining which way the rotary encoder switch is turning, either clockwise or counterclockwise. And once it has determined which direction it's turning, one of two things are going to happen. And this is this part here, going in one direction, and then it looks very, very similar to this bit of code here if it's going in the other direction. But the only difference is here we are adding something because it's going clockwise, and then here we are decrementing something because it's going anti-clockwise. So just looking at one of those, and we'll then go to the other one. So so this function's been called. It's determined that the rotary encoder switch is going clockwise. So we're going to do one of two things. We're either going to increase the frequency, or we're going to move the radix, that little cursor that sits underneath the digit underneath the digits. So that cursor will either move left or right, depending on if the rotary encoder is moving to the left or to the right, in other words, clockwise or anti-clockwise, and if that push switch is low. So here, as you can see, it's got into this function here. It's determined that the knob is being turned, and if the knob is being pushed and we've got a low, it's only going to run this first part. And this first part, as you can see here, if the radix equaled was it 1, 2, 3, 4, 5, 6, 1 megs, it clocks it down. If it's that one, it clocks it down again. So you can just see it basically just decrements it down one by one. Right. And then flips it around if it goes too fast. So it's just going to run around circles. Else, so in other words, no, that push switch was not pushed and is actually still high, it'll do this bit here. So what it's going to do here, it's going to go, okay, that's cool. The frequency equals the current frequency plus the radix, wherever it was the last time radix was adjusted. And if you recall, the default for the start is 1 kilohertz. And then it does a quick test then to make sure that we haven't exceeded our band limits. So if the band equals 0, in other words in 80 meters, it does a quick check. If the frequency has gone beyond or is greater than the 80 meter end limit, or 3900 kilohertz, the frequency will equal 3900 kilohertz. It just hits a wall and won't go any further. If the band was 1 or 40 meters, then it does the same test, but it's using the 40 meter limits. And that's it. So that's all that happens if the switch, so again, if the rotary encoder is moving clockwise. Conversely, if it's going anti-clockwise, I'm not going to talk to any of this, it's this portion of code here that gets enacted. So again, same logic. If the digital read switch is low, it's going to change the position of the radix. It's going to move it in the opposite direction. Else, in other words, no, that is not low. So for the is function, it's an if else. It's going to run this portion of code here. So it's going to go frequency equals frequency minus the radix, because we're now going anti-clockwise on our excuse me, on our rotary encoder. Again, it does exactly the same checks. Is our current frequency less than the 80 meter start? If it is, well, frequency equals the 80 meter start. You can't go any further. You hit the wall. And same logic if you were on, or band equals 1 and you were on 40 meters. Same test. Not going to talk about the rest because that's just part of that function which is trying to work out what is going on with the rotary encoder. And you can see all sorts of things here. You know, there's a glitch, so ignore it, go back to the start, and all this kind of carry on. I will say I've got very used to this way of reading the rotary encoder. I like it. I don't have to have a library. Or, you know, I suspect all of this logic here would be in, or this logic here at least, and the rest of it would be in a library. But for me, I don't require this. It's embedded already in the sketch, and like I say, it's nice and solid and works. Okay, so that's it. So we have. Sorry, I'm sort of bouncing around here a bit. We're in the main loop there. Somebody has rotated. I have rotated the rotary encoder. It's fired off those two, or one of those two interrupt service routines. The frequency has changed, and the for loop's gone through, determined there's a change, and it's now going to do an update display and send the frequency. And those two functions are sitting just below the function which we've just been through, which is reading the rotary encoder switch. And here they go here. So the first one is update display. You know, you can do whatever you like here. The world's your oyster in terms of the display. I've kept it very, very simple. For a start, I'm just setting the cursor on the first row in the first column position. I'm printing then, in fact, what I'm doing first actually, I'm erasing the old frequency by just writing a whole series of blanks, repositioning the cursor back to the start of the line, and then writing the frequency. I then set it to row 1, column 10, and just print, just what they call the vanity call sign. So you can say here double sideband receiver, or whatever you want to put in there. So I've just put Z02CT in. I then move to the first column position in row 1. So that's this, it's typical sort of computer speak. So the second row is called 1, and of course the top row, or row 1, is called 0. Here in fact, this is actually left over from a previous sketch, so that actually is not required. But suffice to say, all I'm doing here now is just repositioning the cursor, so that underline, depending on what am I saying here, on the radix position. Let me just get rid of that, it's not needed. So depending on where the radix, or what the radix is, the value, will determine whereabouts the cursor gets positioned. So it's sitting underneath the applicable digit that's being changed by virtue of rotating the rotary encoder. Apologies if I'm labouring this. I'm just trying to be succinct as I can without rambling too much, which is a problem for me. Anyway, moving on. So having now updated the display, you will recall back up in the main loop, the next thing that was commanded, or the next function that was asked to be executed, was send frequency, and here it is. This is a double side, well, more the point, sorry, this is a direct conversion receiver or transceiver. So there is only one VFO frequency, and that's at our desired frequency of operation. So here we are here. So set frequency, we have to multiply it by 100 ULL just to play nicely with the library for this particular SI5351, and then I'm sending that out through clock 0. So if you recall, there's 3 clocks, or 3 outputs, more the point, on the SI5351 board, 0, 1, and 2. So I'm just outputting that on 0. If this was a super heterodyne receiver or transceiver, and we had both a VFO frequency and a beat frequency, or a BFO, then we would have a couple more lines here where we would set, for example, clock 0 to be our VFO, and then we'd have another line down here setting, say, clock 1. Well, so that's not actually a convention. Like a lot of other people, I would use clock 2 for the beat frequency oscillator. But that's a different story. And that's it. That's all there is by virtue, or in terms of the code. So I apologise for those who know this inside out, back to front, but this is more for those who are sort of getting into the software side of the house. Again, there's, like most things in software, there's many different ways of skinning a cat and doing this. I'm very comfortable now with this sort of format, or this layout, and I've been using this particular sort of layout over and over again, with subtle changes depending on what type of radio it is. But generally speaking, this is how I command, so to speak, the SI5351. This is how I read the rotary encoder, how I change bands, etc., etc. So anyway, that's just going on 28 minutes now, so it's probably way long enough. I will say 73s. Any questions, please sing out, and I will look to dump this code in its entirety on the blog. So if you check out the tags down the bottom, you'll see it there. Okay, 73s all. Cheers all.